Hello friends, welcome to Digital Design using Verilog for Absolute Beginners course. In today's lecture, we will try to understand the meaning of gate level modeling. Digital design, it's a very common practice to use like gate level modeling. So, let us start from the beginning. It's a very well-known fact that Verilog is a popular HDL language used in design and verification of digital systems. HDL, the so-called hardware description language, is a computer-based language that describes the hardware of a digital system. Logic gates like multiplexors, decoders, adders, flip-flops, counters, etc. This Verilog is very much similar to the high-level language C. You have learnt in the first video of this series that the important part of the Verilog structure is the module. Every module has two parts, as you know already. One is declaration part, the other is the body. The declaration part has the name of the module, port list, declaration of the ports, etc. But the most important thing is the body of the module. The body of the module represents the input-output relations. So let us give some attention to this example. In this example, I have given module. Here, the name of the module you get. You can give any name, as I have already told you in the earlier, followed by this list, ports list. And you define what are these ports, which port is input port and which port is output port. Up to this, it is very common. Every student can easily understand this. But the main problem is the body of the module. So what this body represents? The body represents input-output relations, in and out relations. That is how you get the output from the given inputs. Of course, the end is end module. Last one is the end module. Now, representing the body or writing the relations, input-output relations, is the most important thing. This part describes mainly the input-output relations. To describe these input-output relations, different people will follow different methods, which we normally call as abstraction levels. So, now there are 4 abstraction levels or models which are used by the engineers. One is called gate level description model. The other is data flow, or it is also known as continuous assignment model. Third one is procedural assignment or behavioral model. And the fourth one is switch level model. Actually, when you ask any engineer which model is the best, an experienced engineer says no model is the best model. Any wise engineer will use the mix of these models to get the desired result. But generally, there is a common understanding that this switch level model is considered as the lowest abstraction level model, where they use switches like MOSFETs or FETs. And the gate level model description or gate level model is next level. That is, it is also a low level model. In this class, we will concentrate mainly on gate level model. We will understand clearly why it is called gate level model, what is its importance, how to write a Verilog code in gate level model, etc. Let us start. So, this gate level model, some people also call this as structural model. It is popularly known as structural model also, because the Verilog supports basic logic gates as a predefined primitives. Predefined primitives means you need not write any program for these gates. They are readily available, like a book available in your library. You can directly call this. These primitives are instantiated like modules, except that they are predefined in Verilog and do not need a module definition. Very important. Another interesting thing is many of the students will have a doubt about what is this instantiation. Normally the Verilog people, engineers will use this word. Instantiation is nothing but calling, invoking. Because as I just now told you, Verilog has many predefined logic gates. They are already there. The only thing that you have to do is you have to instantiate them. That is, you have to use them or invoke them, call them. Simply calling and using them in your program. That is the meaning of instantiation. So these gates are instantiated to build logic circuits in Verilog. There are two classes of basic gates, as all of us know, AND OR gates, and the next buffer NOT gates. Some of these things you have already covered in your digital design courses. What are these AND OR gates? One is AND, OR, XOR, NAND, NOR, XNOR. I have also given some symbols. Something, this is your AND gate where you have I1, I2 inputs, one output. Normally people call it 2 input AND gate, 2 input OR gate, 2 input XOR gate, 2 input XNOR gate, 2 input NOR gate, 2 input NAND gate, etc. They will have 2 inputs and 1 output. This is the most important thing that every one of you should understand before you write any Verilog code in gate level modeling. So let us consider. These gates are instantiated, means invoked, called to build the logic circuits. Here the simple meaning of instantiation is invoking or calling, as I have repeatedly told you. This is the meaning. Now let us see how we instantiate these gates. For example, suppose I want to use AND gate. How do I call this? Simply write AND, give some name A1. You need not give this also. Simply you can write AND1, AND A1. Within the brackets, you write the ports. Normally in gate level modeling, we use first the output, then the input ports. So that's why I write out I1, I2. If you see the AND gate here, out is the output port, I1, I2 are the inputs. Similarly, I call the NAND gate, NA1, NAND gate 1, out I1, I2. You can see here. Similarly, OR gate, R1, NOR1, out I1, I2, XOR, X1, out I1, I2, XNOR, NX1, out I1, I2. You can see the output inputs. So this is the way of instantiating or calling, simply in a very crude language I can say, using these primitives, pre-existing gates in your design. Now let us take this next type, buffers or not. So similarly, Verilog also provides buffers. It has one input and output. Similarly, NOT gate, which inverts the input. Similarly, we have a state buffer. So they say in the same way as you have seen the OR and gates, here buffer also buffer B1, just name, you can give any, simply you can call buffer 1 or any other name, buffer K, you can give any number, just only two. This is normally called as UUT, unit under test. While writing the test benches, we'll come to that part afterwards. Simply one output, one input, one out, not one output, one input. Similarly, there may be two outputs also, more than two outputs. Then buffer B1 with two outputs. There is a meaning, B1 underscore 2 out, O1, O2, I. O1, O2 are two outputs, I is the input. I think you have understood clearly. Suppose I write a NOT gate. Simply I have not used even here the numbers also. Simply I have written NOT, O, I. That means output, input. That is a legal gate instantiation. So in this way, what we do is we try to invoke, instantiate, that is use these primitive gates to build any logic gate or system. Let us consider now as an example XOR gate. The output of Y of an XOR gate, as all of you know, A complement dot B plus B complement dot A, A complement dot B Y. So here in the gate level model, to implement this design, implement this XOR gate, I have used 4 NAND gates. This is only one method. So because NAND gate is already available, I have used 4 NAND gates, and this is known as XOR gate. NAND 1, NAND 2, NAND 3, NAND 4. Remember the inputs to the NAND 1. A, B are the inputs, C is the output. Similarly for NAND 2, A and C are the inputs, D is the output. NAND 3, C and B are the inputs, E is the NAND 4, final, Y is the output, D and E are the inputs. Here you should remember one interesting thing. When you consider this NAND gate, we have directly inputs A and B. But when you consider NAND 2 and 3, the output of NAND 1 is given to NAND 2. Output of NAND 1 is given to 3. So this is interconnection here. They are represented by wire. When we discuss the data types of Verilog, we'll discuss this in detail. But at present, you can easily understand this is an interconnection. This is not going to be the main input. Here, there is an intermediate input to the NAND 2 from NAND 1. So such values are represented by wire. You remember, we'll discuss this in the next videos while discussing the data types. Now, how I have written? As usual, you know the first part, module. Name of the module is XOR gate. Y is the output, A is the input, B is the input. Final, I am writing A, B are the total inputs for the system. Y is the output, not intermediate. A, B, Y. So, how do I write? Simply module, name of the module, ports Y, A, B. So here I am declaring this input A comma B, output Y. But this is the new thing which you are using first time. Wire, that's what I told, intermediate connection. Wire C comma D comma E. So what are these wires C comma D comma E? You can see the output of NAND 1 is given to NAND 2 and NAND 3 C intermediate. Similarly, the output of NAND 2 is given to NAND 4. I call this D. Output of NAND 3 is given to NAND 4. This is E. So C, D, E are intermediate inputs. So we denote them, we should denote them by the word wire. Always you should remember. So wire C, D, E. Then NAND 1. How you denote this NAND 1? I am instantiating the NAND 1, invoking NAND 1. That is the first NAND gate, NAND 1. Inputs are A, B, output is C. That means I write this as C, A, B. Similarly, NAND 2. I explain this very clearly. One example. NAND 2. D is the output. C, A are inputs. Let us see. NAND 2. D is the output. A, C are the inputs. Similarly, NAND 3. C, B are inputs. E is the output. You see here, E is the output. B, C. What is the last one? NAND 4. So Y, D, E. Let us see. A final output Y. Input is D. This is E. That's what I have written. NAND 4 Y, D, E. Yes. End module. That's what I told. Only explaining this part using the gates that's why it got its name. Gate level modeling or structural model. You are using the structure of these gates. These are all primitives. I repeatedly told you earlier also. These are all already available. You need not write any code. You need not write the behavior of this, how NAND gate behaves. No, not necessary. Simply use the gates. So this, to explain this further, let me consider also one more example, that is to explain the same thing here using what is known as the same XOR gate can also be written as by another method. Can be designed by Aliter means another method. Here I have chosen not 4 NAND gates like earlier. I have chosen one AND gate. Sorry, I am just choosing them as block diagrams. Don't get confused, because I was drawing this simply instead of this using, and simply I have chosen 1 and 2 OR. So how I am designing? I am using 2 input, 2 NOT gates at the input, 1 AND gate, another AND gate, 1 OR gate. Total I have 5 gates, logic gates. So this is another way of designing the same XOR gate. A and B are the inputs, you can see here. So when I write this Verilog code, same inputs, Y is the output, A and B are the inputs. Same. And what are the intermediate? C, D, E are the inputs. Let us see. You can see C, D. What are these things? These are all intermediate inputs. That is, The output of this is given to this. The output of this is given to this. So that's why I have chosen C and D, and E are the intermediate. I'm sorry. Then now let us design not 1. That is, I'm choosing the first not gate. Same way. Yeah. So when I give input A, I get a complement here. For this B big. So how do I define this not gate 1? A complement A, B complement B, second one. Similarly, and C is the output, B A complement. D is the output for this B complement A. Same thing I have done. So because I could not write complement, I have chosen this A complement A, B complement B, and one C B A complement. You can see for this. What are the inputs here? I can use. So B complement A, output is D. B A complement C. Finally, C D are the inputs. Y is the output. Let us check this once again. Yeah. Y is the output, C D are the input. Simply end module. This completes this XOR gate. We can define by different methods. But what is the difference between these two? Earlier, if you come see this, the earlier, here I have used 4 NAND gates. Same XOR gate. People have defined this XOR gate with 5 gates. But which one they prefer? Normally, we require or we prefer the design with less number of gates. And also, what is another advantage of the previous one? Because they are using all the same gates, NAND gates. But here I require 2 NAND gate, 2 NOT gates, 2 AND gates, 1 OR. Therefore, when compared to this method, present method, that is more preferred. Okay, that is the difference between the better or normal. So this earlier one is a better design. That is the actually where your capabilities come out. Similarly, another example, a mux. So gate level example for a mux. For this, what is the output of a mux or a multiplexer? It is a 2:1, 2:1 multiplexer. That means you will have 2 inputs. Out of this, we select 1. For this, you will have a select pin. You will have 2 inputs and 1 output. First, I will show you the block diagram of this. So A and B are the inputs. S is the select pin. Y is the output. Then what is the Y according to digital logic? So Y is equal to A dot S complement. S is the select line plus B dot S select line. Here A dot B means dot you require 1 AND gate. S complement means you require 1 NOT gate. Plus means you require 1 OR gate. Dot as usual AND gate. That means I need 2 AND gates minimum, 1 NOT gate, 1 OR gate. Let us see. The same thing I have written here. So I have chosen 2 AND gates in the gate level model, 1 NOT gate, 1 OR gate. When I give the input CA and select pin here. So what are the inputs to the AND gate? Output is A1, intermediate, input A, S1 are the inputs. S1 complement, NOT gate because. So similarly, B1 output, same select pin yes, input is B, output Y is E. What are the inputs? A1 and B1. It's very, very simple. Let us see the code, Verilog code for this. Simple. As usual, I told you the first one, declare module. Name of the module, I will chosen my mux Y1. A and B here are the inputs. S is also an input select line. Y is the output. You find the difference. Earlier I have chosen output first input. That's why I told you here. There will not be much difference between this. Then we have declared the port. Output Y, input A, B, S. A, B are inputs. S is the select line. Remember wire. That is S1, A1, B1. These are all intermediate inputs. You can see S1, A1, B1. S1, A1, B1. These are the intermediate inputs. They are not direct inputs. So they are all intermediate. That's why wire S1, A1, B1. So what is the first one? NOT gate. S1 output. That is complement. I have called intermediate S1. S is the input select line. First AND gate and 1. A1 output. A and S1 are the inputs. Second AND gate B1 is the output. B and S are the inputs. Final OR gate. Y is the output. A1, B1 are the inputs. End module. So this is the example another example for gate level Verilog code. So by this time, most of you might have got the idea. A better explanation further, I have taken one more example of half adder. We also know that half adder adds two bits which are inputs. The output will be, one will be the sum, the other will be the carry, as you know from your digital electronics. So where sum is given by A XOR B, carry is given by A and logic and B. A and B are inputs. So what do I require? I require one XOR gate, one AND gate. Simply I have to instantiate these things. Now let us see the example, and I have given the truth table also. I have chosen one XOR gate, one AND gate. A and B are the inputs. Straightforward example. So A and B are the input, means what will be the output sum? A XOR B, that is A complement dot B plus B complement dot A. What is the carry? A dot B. So let us see this through the simple code, Verilog code. First, same module. I have given some name. My HA means my half adder one. Similarly, S, C are the outputs here. Sum, carry, A and B are the inputs. Then declaring the inputs as A comma B, output S comma C. Then what is the instantiation? XOR1. First XOR gate is S is the output, A comma B are the inputs. Similarly for the carry AND gate, C is the carry, A comma B is the inputs, C is the output. So simple end module. So this completes the half adder. In the same way, I have also given a full adder. You can go through this, where I have two inputs A, B, and carry in is the third input. I have one sum and one carry, which you know A XOR B, XOR C in, carry in from these two. Similarly out, carry out, A dot B, B dot C in plus C dot CIN dot A, carry in dot A. So for this I require two XOR gates, 3 AND gates, OR gate. So let us see how we do this. Same way, it appears slightly complex, but if you observe carefully, it will not be any problem. Two XOR gates, 3 AND gates as usual, which normally gives the carry out. This will be OR, finally sum. So on the same lines, you can understand this code also. I declared first module name, ports, declaration, where D, E, F, Z. You can see here D, output of this is. So next E, F, Z. So this is only a 3 input OR gate I am using. So these are the wires which we call D, E, F, Z. Same, first XOR1 gate, D is the output, A, B are inputs, S, E, A and E. So on the same lines, you can understand easily this code and 3. Finally, R1, it gives carry out is E, F, Z. Sum is, here you can understand D, comma, C in. You can see in the diagram. Carry out is E, F, G. C out, E, F, Z, OR gate. Sum, XOR D, comma, C in. S is the sum. That's how you can represent what is known as this gate level module. So when you choose this gate level module, we use or we instantiate simply the gates. So for a beginner, this will be the easy way, as long as the system, digital system is a simple. But once the system becomes complex, it cannot be possible. That means it will be a little bit difficult. So this is about the introduction and explanation of the gate level modeling, and I hope all of you have understood clearly. You just go through the video once or twice and practice this with some examples. Thank you for watching the video.